Some useful structural information can be obtained by examining a mass spectrum of a compound. For example, the molecular mass of the molecule is revealed by the weight of the M peak, which is the molecular ion, which is usually pointed out to you in the spectrum. You can also get some useful information by looking at the mass of fragments that are lost from the M peak. M-15 would be a loss of a methyl. M-17 would be loss of OH. It's also possible to look for the presence of bromine or chlorine in the molecule, and by looking at whether or not the molecular ion is odd or even, you can determine the presence of a nitrogen in a molecule, or whether you have an even or odd number of nitrogens in a molecule. Remember, you don't have to identify every peak in the mass spectrum. You are just looking for key peaks and key mass losses from the molecular ion. The mass spectrometer shoots a beam of high-energy electrons at a molecule. It will displace an electron from the molecule, generating a molecular ion, which then breaks into fragments, and the spectrometer tells you the mass of each of those fragments, from which you can deduce certain things about the molecule's structure. Thus, the function of the mass spectrometer is the detection of the masses of cations. And the mass spectrum itself is a plot of the amount of each cation present, that is its relative abundance, versus its mass to charge ratio, its charge, which is always going to be +1. An example of a mass spectrum is shown here for methane. The tallest peak in the spectrum is, in any mass spectrum, is called the base peak, and for methane it happens to also be the M peak, the molecular ion, which isn't always going to be the case. About 99% of carbon atoms have a mass of 12, and about 1% have a mass of 13. So therefore, the peak at 17, which is shown here, is referred to as the M+1 peak, and that's due to the isotope of the other isotope of carbon that's present. One thing I want to point out also is that mass spectrometry occurs in the gas phase, and in the gas phase you will see species that exist that don't normally exist in the solution phase. For example, here we see peaks for CH2, CH, and even C, things you would never ever see in solution chemistry, but they exist in the high energy world in the gas phase. The typical mass spectrum is shown here. This one is for decane. You can see that on this axis we have the M to Z, or mass to charge ratio, which indicates the mass of the ions that are present, and on this axis you have the relative intensity, or which corresponds to the relative amount of each of these fragments that are present. The molecular ion M peak or M plus peak is indicated here, which corresponds to the molecular weight of decane. You'll also see the molecule fragmenting with losses of ethyl, propyl, butyl, pentyl indicated on the spectrum. Therefore, by looking at the mass of fragments that are lost from the molecular ion, subtracted from the molecular ion, you can get some structural information about the molecule. In this particular case, for example, we have the molecular ion, and then it loses 15, a mass of 15, which indicates the presence of methyl in the molecule. It also has a loss of 29, which can correspond to the loss of an ethyl. And you can see that we have a peak at 57, which corresponds to a butyl, T-butyl in this case. We'll now examine some common fragmentation patterns of alcohols and also ketones. The molecular ion of an alcohol can readily undergo what's called alpha cleavage, where you're breaking the bond between a substituent on the carbon bearing OH and that group. This leads to a resonance stabilized carbocation. Alcohols also undergo dehydration with the loss of H2O, that is 18 from the molecular ion. We can see all of this alpha cleavage occurring in the mass spectrum of 2-hexanol, which has a molecular weight of 102. Here's the mass, 102. There's also a peak 1 unit below that. That's the M-1 peak, which results from a secondary alcohol losing a hydrogen off of the carbon-bearing OH. So this is an alpha cleavage where a hydrogen is being lost, leading to a resonance stabilized cation. Frequently, the base peak for alcohols is the alpha cleavage where the largest substituent is being lost. The largest mass is being lost. And that's indicated here. Alpha cleavage, this is the largest substituent, and we end up with a resonance stabilized base peak. We also actually see a cation present resulting from the loss of that large substituent. Also present are typical M-18, that is M-H2O, and also in this case, because of the fact that we have alpha cleavage affording the loss of a methyl, we see the loss of a methyl as well. Similar sort of peaks can be seen in the mass spectrum of 2-pentanol. The molecular ion is very, very small and can hardly be detected. However, you can see present M-15, you can see M-water, and you can also see a peak which corresponds to loss of water and loss of a methyl group. The base peak results from alpha cleavage here, where the largest group is being lost. In the case of ketones, alpha cleavage is also predominant, and once again, the largest alpha substituent is most readily cleaved, and that can be seen in the spectrum of 2-pentanone. This is the M peak, which is the molecular weight of 2-pentanone. You can see that alpha cleavage, where the largest substituent is lost, gives you the base peak of 43 with loss of propyl. Also present is alpha cleavage with the smaller group being lost, and you have M-15. Here we have the mass spectrum of a compound that is an isomer of 2-pentanone and has no proton NMR peaks greater than 2.5 parts per million. Let's try to identify this structure and also assign some of the fragments in the spectrum. What does this tell us? No proton NMR peaks greater than 2.5 parts per million. Well, an isomer of 2-pentanone could be an aldehyde, where the carbonyl was at the end of the chain. If there are no peaks greater than 2.5 parts per million, this could not be an aldehyde. So remember, it's an isomer that contains a carbonyl, which means that it could be a carbonyl on carbon 1, could be on carbon 3, but it's not the one on carbon 1, because that would be an aldehyde, and aldehydes have peaks between 9 and 10 parts per million. What are some of the peaks we can identify in the spectrum? And displayed here for assistance are some common fragment ions and also masses lost from the molecular ion. Well, probably it's easiest to point out the molecular ion. We know that from the previous page that 2-pentanone has a molecular weight of 86. What else do we see? We also see loss of 29, which means that an ethyl group is most likely present. If that's the case, the structure must be 3-pentanone. And what you're seeing, it's a symmetrical molecule, is when you have alpha cleavage, you end up with a peak at 57, which is for this resonance stabilized cation. We also see a peak at 29, which corresponds to the ethyl cation. Mass spectrometry can be very useful for detecting the presence or confirming the presence of a bromine or a chlorine in the molecule. Mass spectrometers separate and detect individual ions, even those that differ only by a single atomic mass unit. We saw that in the spectrum of methane earlier in the video, where we saw a peak for carbon-12 and we also saw a peak for carbon-13. This type of isotope identification is most apparent when the molecule has a bromine or chlorine present, because in the case of bromine, you have two abundant isotopes of almost equal abundance, bromine 79 and bromine 81. Therefore, their peaks in the mass spectrum will have an almost equal intensity. For chlorine, the two most abundant isotopes are chlorine 35 and chlorine 37, and their relative abundance is 3 to 1, respectively. That can be seen in the mass spectrum of 2-chloropropane, which is shown on this page. Note that you have this 3 to 1 ratio pattern of the M and M plus 2 peaks for the molecular ion, and that's because one peak is due to the molecular ion for the molecule that has the isotope 35 of chlorine, and the other peak is due to the presence of the molecular ion where the isotope of chlorine is 37. You'll also notice typical patterns of M-15, but when you lose 15 a methyl from this, you still have chlorine present in the molecule, so you can see that the peaks at 63 and 65 are due to these two species, where you've lost a methyl, but you still have a chlorine 35 and you have a chlorine 37. You also have, finally, you have loss of a chlorine, which is M-35 from the 78, and that is for the propyl cation. The presence of both isotopes of bromine can easily be seen in the mass spectrum of 1-bromopropane, where you have the molecular ion for bromine 79 at 122 and the molecular ion that has bromine 81 at 124. And notice these two peaks are almost of equal intensity. When you lose 15 from this, you still have bromine present, and you can see there are two peaks at 107 and 109 corresponding to the two isotopes of bromine that are still present in the molecule. 122 minus 43 is 79, which is loss of bromine, giving you the propyl fragment. Compounds that contain only carbon, hydrogen, oxygen, and halogen will always have an even nominal mass, which is the sum of the most abundant isotopes. So when you're adding up all of the masses, you use the most abundant isotope of the halogen, and therefore these molecules will always have an even molecular ion. If you have an odd molecular ion, this will generally indicate the presence of a nitrogen. This is called the nitrogen rule. So compounds with an odd number of nitrogens will have an odd molecular ion. Compounds that have no nitrogen, or if they have an even number of nitrogen atoms, will have an even molecular ion. So two examples are shown here on this page from some common natural products, nicotine and dopamine. Notice that nicotine has two nitrogens, and it has an even number of nitrogens, so I have an even molecular weight and an even molecular ion. The mass of the molecular ion is an even number. For dopamine, there's only one nitrogen present. It's an odd number of nitrogens, 1, which equals an odd molecular weight, which is an odd molecular ion, 153. So these are some clues you can look at when you are examining the mass of the molecular ion of a compound that you suspect might have a nitrogen. Remember that when you're analyzing a mass spectrum, there is no need to identify every peak. It's not like proton NMR or carbon NMR. It's more like IR, where you're looking for key peaks and also the loss of common structural fragments in the case of mass spectra. You normally won't use mass spectrometry alone to identify a compound with an unknown structure. It's usually provided as supplemental information. You'll use it along with things like NMR data or IR data and molecular formula. On this page are shown 3 mass spectra and 3 chemical structures. Which mass spectra belongs to each of these 3 compounds that contain carbon, hydrogen, and oxygen? Which of the 3 compounds do you think it's easiest to identify or match its mass spectrum to? I think probably THF. Why is that? Because the other 2 have molecular weights of 100, whereas THF has a molecular weight of 72. In each of the spectra, the M peak, the molecular ion, is indicated. This has a molecular ion of 100, this at 100, therefore their masses are 100, and this is at 72. So therefore, this has to be THF. What about this one? It has a molecular ion at 100, so it has to be one of these 2. Now you have to use some information that you have already seen about common fragments lost and fragmentation of alcohols and ketones. Here we see loss of 15. This compound could not lose 15 because there are no methyls in the molecule. We can identify some of the fragments in the remaining mass spectrum. We have the molecular ion losing 18, which is loss of H2O. This would not lose H2O. Alcohols typically lose H2O.